In this video, we continue looking at the proof of the second isomorphism theorem for rings. In the previous video, we found out that I was an ideal in the subring S plus I, and as a consequence, the quotient ring for this side of the diamond, which is S plus I mod I, is well defined. And we also found out that S intersect I is an ideal inside the subring S, and so the quotient ring for this particular side of my diamond is also well defined, and that would be the quotient ring S mod S intersect I. And the statement of the second isomorphism theorem says these two quotient rings are isomorphic. Now, in the previous video, we discovered the following things. The first thing that we discovered was that the elements of S plus I mod I were nothing more than the left cosets of I that happen to have representatives pulled from the subring S. And the other thing that we did is we defined a map phi from the quotient ring S plus I mod I to the quotient ring S mod S intersect I by the formula phi of little s plus I was just going to be little s plus S intersect I. Now, since cosets have multiple names, the first task that we must do in trying to prove the second isomorphism theorem for rings is we need to show that phi is well defined. So let's actually look at that particular problem. Saying that phi is well defined means that we have this setup. We want to let S1 plus I be equal to S2 plus I inside capital S plus I mod I. Now, we need to show that in spite of those two different names for the same coset, that phi sends them to the same place. And before actually doing that, there are several things that I want to kind of make a list of what I know. So in this particular thing, since I know that since S1 plus I is equal to S2 plus I, we're going to know that S1 minus S2 definitely belongs to I, and that's because of coset equality. So by coset equality. But we also know that we also know something else here. We know that S1 and S2 are both pulled from S, since the elements of S plus I mod I are equal to the left cosets of I, where the representative is pulled from S. And S is a subring, so this fact here tells us that S1 minus S2 also belongs to S, and that's because S is a subring of our main ring R. And what this tells me is that we have two interesting facts. We have S1 minus S2 is inside I, and we have S1 minus S2 is inside S. Well, as a consequence, we do know that S1 minus S2 now belongs to S intersect I, and that's going to be important. So let's look at this now. So now look at this. Let's see. Phi of S1 plus I is just S1 plus S intersect I. And that looks kind of funny, so let me clean up my notation there. And phi of S2 plus I is nothing more than S2 plus S intersect I. And I also want to note that we've already seen, so I'm going to say that we already know, S1 minus S2 lives inside S intersect I. And that particular fact says something really important. That fact says S1 plus S intersect I and S2 plus S intersect I are one in the same coset. So as a consequence, these two sets are the same coset. They are equal. And what that means is that we can say phi is indeed well defined. We will continue this proof in the next video.